Okay, so we're working on this little funny geometry problem with vectors in R2, just to remember how these inner products work, or also called dot products. I'm going to call them inner products because I guess that's what everyone calls them once you're working with them in general. So normally the dot product is only on R2. So calculate the length of some vector x minus 3y using what you know about x and y. And let's see what you guys said. Reveal counts. 2, 3, 4, 7. 5 people said 7. So out of 10 people, 5 people said 7. 7 is the right answer. So if you said 7, you probably remember how this stuff works. If you have a different number, then let me refresh your memory on how these things work. So you have vectors in R2. There's like x and y, and they are both unit vectors. A unit vector we would write as the norm. This is in R2. The norm squared is equal to 1. The norm squared of y equals 1. But in R2, or in Rn more generally, or in any number of dimensions, I picked R2 so we could draw nice pictures of it on our two-dimensional screen. But in any R to the d, you have these vectors, and you also have an inner product, which is things like this. X, y, right, is x1, y1 plus x2, y2 plus dot, 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 plus xd, yd. That's in Rd. We're in R2, so we only have the first two. And when you want to compute a length of something, that is the inner product with itself. So this is like the key thing that we have. The inner product with itself is x1 squared plus x2 squared is the sum of the two components. Let's work with in d equals 2 from now on. And so you can do the inner product of something with itself to get the length. And so what the question was secretly asking you, please find the length of x minus 3y squared, and that's the inner product of x minus 3y with itself. Okay, I'm going to stop writing the vector signs because I guess I'm lazy. Okay, so that's what you had to do. And the nice thing about the inner products is they play nice with algebra. You can factor things out. They're so-called bilinear, so they're kind of like linear in either factor. So you can expand this out the same way you would expand out x minus 3y squared, right? Like this is like a side note, like this is completely unrelated. You can't actually do x minus 3y squared because they're vectors. Okay, let me put the vectors back in. Right, like this doesn't make any sense. You can't square a vector. But whatever the rules are for doing x minus 3y squared, the same rules apply to the inner product because they're both bilinear. Okay, and so you, after expanding it out, you should get xx. Let me write them out properly. 3yx. Actually, why don't I leave the 3 in for now? 3y. That's this one. That one. This one is minus x with 3y, and then you have minus 3y with itself, plus negative 3y, negative 3y. And then you can expand them out even more. You can pull all the constants out. So this is x with itself, x, and then you have minus 3yx, minus 3xy, and then these two negative 3's together give a plus 9yy. Okay. And now you know things about the vectors. You know they are unit vectors, so x with itself is the norm of x squared, which is 1. Y with itself is a unit vector, so that is 1. So this is that y equals the norm of y squared is 1. And in the middle, you have the inner product of x and y and x, but I told you that in the question that was a half. In fact, one thing you could do is you could combine these together for real valued things. The inner product of xy equals yx. And so you could say this is minus 2 times 3 times xy, because there's two copies, and the xy is a half. So you get 1 minus 2 times 3 times a half plus 9. Okay, so that's 10 minus 3, which is 7. Okay, so probably lots of people did that. Of course, you can also kind of look at the picture, like, and think about this geometrically. You got x, and then you have like y is some angle over here, and you can think about 3 copies of y, and what does it mean if you do x minus 3 copies of y, and then you can like figure it all out. But it is just geometry, like all the geometry is baked into the algebra, which is the beautiful thing about the inner products. So you should get kind of comfortable with these kinds of manipulations, because that's what we're doing now. Yeah.
Do you change like the sign when you switch the x and y?
Like in this little thing, when they are like this, no, don't cross it out, highlight it, okay. That?
Yeah.
So if they're real valued, it's literally equal. So in R2, we're about to do them, they're gonna be complex valued. And then you're gonna see that you have to do a complex conjugate. But for almost everything, like the real value is good enough. But the textbook does complex, and like there's some things where it's nice to do complex. So we'll do the complex version, but essentially it's the same. You'll see there's a complex conjugate. Yeah, great question. Anyone else for questions about this? So where do you guys learn this stuff? I guess it was like high school. Yeah, what?
Now that I remember, this exact thing came up in like the last couple weeks of the Algebra 2.
Okay, yes, okay, exactly. All right, that's another place where you should do it, sort of in general for any vector space or something, right? Okay, great. Yeah, finite dimensional. Right. Okay, fantastic. Okay, so why am I telling you all this? Because today we're starting chapter 3, and chapter 3 is on inner product spaces. And just like we had a normed vector space in chapter 1, which we then sort of like spent a lot of time in chapter 2 building as integrable functions, now we're going to have an inner product space. So chapter 3, inner product spaces. Inner product spaces. So just like before, when we had a vector space with a norm, now we're going to have a vector space with an inner product. And what is an inner product? I have to give you the definition. If I can find where it is. Okay. So this is definition 3.2.1. And there's an A, a B, a C, and a D, and so on. A says the inner product of x and y must be the complex conjugate of yx. So yx bar. So of course, if everything is real valued, then when you do the complex conjugate, nothing changes. As a reminder, the complex conjugate, you swap I with minus I. But when things are real valued, it doesn't do anything. When things are complex valued, it's the complex conjugate. So I guess maybe more technical, dot comma dot is a map from V cross V to C, right? So the inner product of two things, you take two vectors, you do their inner product, you get some complex valued thing. And these are the properties it has to satisfy. So one is flipping it like this, you get a complex conjugate. Another thing is linearity, alpha x plus beta y with z equals alpha xz plus beta yz. So it's linear. If the second component is fixed as some fixed vector z, then it's linear in the first component. Sometimes you'll see people write, oh, it's also linear in the second component. But in this textbook, they don't write that. Does anyone have a guess why why don't we have to write down that it's linear in the second component? Yeah?
The first property kind of implies it to be at least conjugate when you're on it.
Right, exactly. So but if you have A and B together, then it's automatically, you can do anything you want in the second component because you flip it by part A and then you flip it back by part B. So also, this is not in the textbook, but also if you do z with alpha x plus beta y, it's going to be zx and zy. But the thing is, because of the complex conjugate, when you do this complex conjugate flipping, anything in the second component, when it comes out, is going to have a complex conjugate. So it's going to be alpha bar, and beta bar. So the textbook doesn't write that, but they definitely use it later and assume that you know it. So worth thinking about. Okay. So those are the properties that we want. Then we have the typical things. Oh, I guess the whole point is we want the norm of x squared to be the norm of x, inner product of x with itself. So we better also ask for the norm of x with itself is greater than or equal to 0. And last but not least, the norm of x with itself equals 0 if and only if x equals the 0 vector. Right? So these are very similar to our properties of norms. We can't have it be a negative number. And so when you have all these properties, you can define a norm, which is the norm given by the inner product, like this. So define norm. And norm, if the inner product satisfies definition 3.2.1, then the norm will automatically satisfy all the stuff from the inner product space in chapter 1. So this is like, we learned about normed spaces, and inner product spaces are a special type of normed space where everything we did before still applies, but now we have this extra little bit. We have this extra thing we can do, which is we can take the inner product of any two variables. Okay. I'll give you the examples you should have in mind, and we've seen one of them already, which is r to the d, right? And that is where like all of your intuition will come from, or even r2. So you think of these things as vectors, and the inner product is like measuring how aligned they are, right? If they have an inner product, if the angle between them is 0, then their inner product is like the product of the lengths. If the angle between them is 90 degrees, the inner product is 0. Like this is a great intuition that you should always keep in mind here. So this is x with y is the sum of the individual components, k equals 1 to d of xk, yk. That's the inner product on Rd. So Rd is an inner product space. There's another space called little l2. Little l2 is the sequences, so it's the set of sequences such that the sum from k equals 1 to infinity, let's say A is the sequence AK, k going from 1 to infinity, and the sum of the squares of the AK should be less than infinity. So that's little l2. Little l means sequences, and the inner product on this space, you can probably guess what it is. If you have two sequences A and B, then this thing will be the infinite sum AK times BK. Oh, and this is going to happen very often. I'm used to thinking about real valued things. Because the textbook does things complex valued, you have to put a bar always over the second component. Okay? And then when I write AK squared, it's going to be the norm of AK squared. So if, let's not write norm, let's write absolute value. Okay. So I'm sure I will forget many times. So if AK is a complex valued thing, it's not that the sum of the values squared are finite, it's the sum of the length of the complex number squared. So of course, if it's a real number, the squaring it or taking the absolute value and squaring it are exactly the same. But if it's a complex number and you square it, you get some other complex number. Like I squared is -1, that's not good. We want the absolute value of I, which is 1, then square. I'm gonna forget a ton of times. Try to remind me. We're gonna do like one example later with complex numbers, but I thought might as well do what the textbook does. Okay, so those are the two examples. Does anyone know another example of a space, a vector space that is interesting to study that might have an inner product? Yeah.
Functions.
Yeah, functions. Which functions though?
Real.
Yeah.
Complex.
Real. Okay, so they're real valued. So f from into something into R. What do you want their domain to be?
The functions. No.
Yeah. What should the domain of the functions be?
C.
C is bad because we don't know how to integrate over C.
With Banach space?
Well, the space of functions is going to be a Banach space. I just want to know what is the domain that you want.
R.
R is good. Yes. Okay. Very good. Another acceptable answer would be like any interval. Maybe I'll say minus pi to pi. Who knows why I'm saying minus pi to pi? Okay. Okay. So that's a space of functions. That is the vector space we've been studying since day one. What is the inner product? So if you have f and g, how do you do f and g? Is what? What would that be? Anyone? You're doing some symbols in the air. You're probably close to the right answer. What do you think it is?
It's the integral of minus L to L of f of x just times g of x.
Yeah, times g of x. Beautiful. Yes. And this is what we did on day one. So this is the inner product on functions. Is you multiply the two functions together and integrate them. Of course, the integral better be finite, and like right, it needs to make sense. So what space of functions is this? It turns out it's the space L2. This is the space L2. So you can't look at all possible functions, because then you do the inner product of two things, that's infinity, that's not a number, that's not allowed. But if you only look at the functions in L2, then it's all good. So we're going to look at L2, and let's say of minus L to L. I can't call it L because we're going to get confused on what L means. Okay, let's call it L2 either of R or L2 from minus pi to pi. And so that sets the domain of the functions. and you want them to be L2 functions. So the integral of f squared dx has to be less than infinity. Okay, and then once again, if you want to match the textbook and you want to do complex numbers, you got to put absolute values and bars in the right places. So what is the inner product if they're complex valued? It's f times g bar. And what is the norm? It's not f squared, it's the absolute value of f squared. So if f is complex valued, then you got to worry about that. Okay, but that's the main example that we want to do, is the space L2, and everything we did for integrals in chapter 2 will still apply, right? We're still going to have the convergence and all that stuff. And limits will still work with our integrals because we developed the limiting integral. But now we have an extra thing we can do. Before we could take the norm, now we can also take the inner product. And that's going to help us out tremendously. Okay. All right. Any questions or comments at this point? Okay. So I'm going to give you some definitions. These definitions technically come later in the textbook, but I want to give them to you now so you can see why things are useful instead of doing a bunch of theory before we get to it. Definition 3.4.1, so like way in section 4, is the definition of orthogonal. Orthogonal, which is a great $1 million word. Orthogonal. And it means, so two vectors are orthogonal means, and we're going to call the vectors like x and y and that kind of thing. X, y are orthogonal means the inner product of x, y equals 0. Okay? And this is essentially, most of the use of inner products is because things can be orthogonal. And when things are orthogonal, everything tremendously simplifies. It's like so much easier. Like your life goes from miserable to like so beautiful and nice. And the reason really is fundamentally what I showed you on the first day of class, which is that if the x's, if you have a sequence x1, x2, xn, and they are orthogonal, then you can write linear combinations of the x's to make anything you want by doing the inner products. Then, if the sum of alpha k times xk equals x, k equals 1 to n, then alpha k equals the norm of x with xk. Okay, and I guess xk with x. Okay, you know what? I'm not gonna worry about it. Let's just leave it. Once again, I'm gonna make lots of mistakes with the bars. I'm pretty sure it should be the other way. Xk with x. Okay, fine. Let's fix it. Xk with x. I can't bring myself to care about the complex numbers. Okay. All right. Is that right? Yeah. Okay. So why is this true? Because if they're orthogonal, you do the inner product of this thing. You take both sides, you inner product of xk, and then almost every single thing in the sum here will be 0, and you'll just have one term left over, and that term will be alpha k, and then on the right-hand side you have xk with x. Oh, these aren't orthogonal. These are orthonormal. Let me write orthonormal. I'll give you the definition for that as well. Orthonormal means orthogonal and the norm of x equals 1. So the normal part means they are normalized to be size 1. So orthogonal, everything is perpendicular to everything else, and orthonormal is and they're also equal to length 1. Okay, so essentially what we are going to do is we're going to build up a big theory of what happens when you start putting infinities for the number of orthogonal things. So you just have like finitely many orthogonal things. That's exactly what you do in linear algebra class. There's some dimension d, it's Rd, and you can talk about these things, and everything is like perfectly fine. But in our class, we're going to take n to infinity, and then it's going to get real nasty with like the analysis. Are they converging? Are they not converging? That's what we're going to worry about. So this is essentially what we want to do. And I'm going to give you 2 examples of orthonormal things. Orthonormal things on our spaces. So in little L2, which are the sequences, here's a nice orthonormal sequence. En is the sequence which is all zeros, all zeros, and then it has a single one in the nth slot, nth component. And then it's all zeros after that. So this is a sequence that ends with all zeros. That's En. And if you look at them, what is the inner product of En with Em? Well, the inner product says you add up all the components, right? So bring over some other En, which is going to have all zeros, and then it's going to have a 1 in the mth component. Okay, and it has all zeros everywhere else. What happens when you multiply the entries of En with Em? Well, either they're both 0, or one of them is 0 and the other one is a 1, or there's one other situation where one of them is a 1 and the other one is a 0, but you're going to have a whole bunch of zeros. So this is 0 if n is not equal to m, and actually it's 1 if n equals m. They're orthonormal. They're also length 1. So that's a nice example of an orthonormal sequence. And in fact, every time you write a sequence down in little L2, you're actually the sequence alpha 1, alpha 2, alpha 3, dot, 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 dot. This is some sequence. You could write this sequence as the linear combination n equals 1 to infinity alpha n times En, right? Because an alpha 1 in the first component is saying, take the sequence that's 1 with all zeros and then multiply that by alpha 1. Take the sequence that has a 1 in the second component, multiply that by alpha 2. Take the sequence that has a 1 in the third component, add them all up, right? And this makes perfect sense. Like, even though I put an infinity here, it's really not that scary for the En, and everything was going to make perfect sense the way you think it does. But actually, things will get complicated. Like, for other sequences, this infinity is quite tricky. So maybe for now, this is like coming up. Like, you should be scared of this infinity. You probably are. Okay. Will make sense of the infinity. That's our goal. That's what we're doing in this course. Okay. That's little L2 with like a very standard basis. This is like the basis everybody knows. In capital L2, let's do L2 of minus pi to pi. And the reason I want to do minus pi to pi is if we do minus pi to pi, here is a sequence of vectors. Let's call it S for sine. Sn of x will be the function sine of nx. So sine of x, sine of 2x, sine of 3x. And if you calculate, let's calculate what is the integral of Sn of x. Sm of x. That's the inner product with Sn is the integral from minus pi to pi of sine of nx sine of mx dx. That will again turn out to be, and we did it in the first day of class, it's some integral you can do using trig identities if you want. There's many ways to do this integral, but it's 0 if n is not equal to m. And that's because when n is not equal to m, the sine functions kind of like go up and down kind of distinctly from one another. So when you multiply them together, you're going to have an equal number of parts where it's positive, an equal number of parts where it's negative, and you multiply them together and integrate, on average it's 0, integrates to 0. But when n equals m, if n equals m, then you have the integral of sine squared, right? And the integral of sine squared, by that trick we saw on the first day of class, the integral of sine squared is half the length of the integral. Because on average, sine squared is half. So the integral will be a half times 2 pi, also known as pi. So are these things orthonormal? No, they're not. Are they orthogonal? Yes, right? Between any two different ones, the inner product is 0. They're not orthonormal. If you want to make them orthonormal, you should look at the sequence 1 over square root of pi times the sine of nx. This sequence will be orthonormal. I don't know, what do you want to call this? S hat of n. Hat means normalized. This is S of x divided by the norm of S of Sn, right? So from this, the norm of Sn squared is pi, and so the norm of Sn equals the square root of pi. That's the inner product with itself. Okay, and this is now it's an orthonormal sequence. And now you can reasonably ask, if I have some function, can I write it as the infinite sum of these sine functions? That's what a Fourier series is, and that's what we're going to get to. Maybe, okay, well, do you guys think we can write a function as a sum of these sine functions? Do you think it'll work? Some people are nodding. There's a trick, it won't work. There's an obvious thing that you need to add on. Just the sines on their own, yeah. Cosines, yeah. So the sines on their own are not enough. You're forgetting a whole slew of functions, which are the cosines. And together, the sines and the cosines can write everything. But on the face of it, this is why it's so tricky when you move to infinite dimensions, right? When you're in finite dimensions, you're like, look, I wanted to write things in this d-dimensional space. I got d things, it's going to work out. Now we're in an infinite dimensional space. I got infinitely many things, but it turns out I forgot half of them, right? So like that's why it's a lot harder to make sure you have everything and to make sure it works. And the proofs are harder too. So the sines on their own won't be enough. The sines plus the cosines, that will be enough, and that's what we're going to prove. Okay, let's start proving some useful results. Any questions or comments before we? Yeah.
Up above, you wrote for orthogonal vectors that you can write the coefficients as that inner product.
Yeah.
Is that for orthonormal or orthogonal?
Oh, that was orthonormal. Yes, very good. Thank you. This is very good. Otherwise, okay, why don't I write it like this? You divide by xk. And then if xk equals 1, then you're dividing by 1. That way we'll cover our bases. Yeah, great comment. Yeah.
Is there an example of something where the dot product or the unit product is 0 and it's not orthogonal?
I'm not sure I understand. Say it one more time.
Well, okay, I guess, or not, sorry, I asked the question totally wrong. Is there an example of something where the dot product is 0 and the norms are not 1?
Yeah, I just gave you one, right? These S functions, right?
Again, okay.
Right. So, and actually, okay, it really is like a convenience thing. Like the orthonormal things are nice to work with, because then when you do this algebra, you just don't have to divide, just like I forgot to divide by this.
Okay.
But it really is like, there's no like magical significance about orthonormal. It's like we took orthogonal, we made it more convenient for ourselves by dividing by the square root of pi. We just divided by that so that we don't need to worry about it. It really is just like pure convenience to make the like work a little bit nicer and easier. Everything would still work with orthogonal. You just got to remember to always divide by the stupid square root of the norm. And so like we don't want to do that. Yeah, it's a great point though. Okay, anyone else? These are great. Okay, let's prove some useful results as we like build up towards this thing. And this is one of the coolest, most used theorems in all of mathematics, which is in the book. It's called Theorem 3.2.9. In the book, it's called the Schwarz inequality, but of course, most people call it the Cauchy-Schwarz inequality. And I've heard nowadays there's like some other person I'm supposed to add on as well who also like discovered it in the 1400s or whatever. So the somebody Cauchy-Schwarz theorem, you guys can look it up and tell me if I'm forgetting to properly credit someone. The Cauchy-Schwarz inequality. And it says that if you have two vectors and you do their inner product, it can't be longer than the length of the vectors. All right? And so it says the absolute value of xy is less than the norm of x times the norm of y. Okay? And this is kind of why, by the way, this is kind of why sometimes people will write things like xy equals the cosine of theta times the norm of x, norm of y. This is like a little aside. And the reason this is like a well-defined thing is like cosine of theta is between -1 and 1. So whatever number this is, it's some multiple of norm of x, norm of y, and that multiple is always less than or equal to 1 in absolute value. So it's always between -1 and 1, and so you can always do this. So by the Cauchy-Schwarz inequality, you can kind of make up a cosine for any two things that you can do the inner product of. You can say, what is the angle between the function sine of 2x and the function sine of 3x? Okay, well the angle is 90 degrees because they're orthogonal, right? That's why the angle is 90 degrees. To make this equation work, you put in cosine of 90 degrees and you get the inner product equals 0. So the Cauchy-Schwarz inequality lets you understand these things as angles. Yeah?
Would the absolute value also work instead, like with just the norm?
Oh, if it's real value, then it's fine. You can drop the absolute value. But again, if it's complex value, then you need to put the thing there, right? Because if the inner product is like I, that's not the cosine of anything.
What
Yeah.
if it's norm x times
Norm of, you want to multiply the vectors x and y and then take the norm? You're not allowed to multiply vectors. You go to jail, yeah. Yeah, remember, so we're in a vector space. The only thing you're allowed to do is add them and do scalar multiplication. If you want to multiply them, that's called an algebra, and then you have to take a different course. Yeah. Yeah. No, it's a good point because like we're actually doing functions, right? And functions are an algebra. So this whole time we're pretending that you can't multiply them, but of course you can multiply two functions together, right? So it's just that when you multiply them together, we don't know what will happen. And so in fact, if you take two functions, each of which are integrable, and you multiply them together, then the product of them, we don't know if it's integrable anymore, right? We would need some way to control that. So like all the stuff we want to do, like won't work when you start multiplying them together. Yeah, and I guess the inner product space is some kind of way of weakening, right? Because you can multiply them together only for doing the inner product. So it's like the inner product is like allowing us to sneak in a little bit of multiplication in a way that we can control and be happy with. By the way, that's the reason why we have to work in L2, not in L1, is it lets us define the inner product. In L1, it wouldn't work, exactly for the reason that when you multiply two L1 functions, it might not be integrable anymore. When you multiply two L2 functions, because each function individually is square integrable, it will be okay. Actually, we're going to prove that in a second. That's the proof of the theorem. Okay, great question. Anyone else? Yeah, the longer you can make me talk after you ask a question, the better the question must have been. Okay. That's actually not true. There's many excellent questions that are like, did you mean to write an I over there? And I'm like, no, it was a J. Actually, I got like 4 questions total in my PhD defense, one of which was the following. The whole talk is about these things called non-intersecting walks, and they like don't intersect, okay? They like repel each other. One of the questions was, in that diagram, right there, it looks like they're intersecting. What's going on? I'm like, no, they're just like an inch apart, like they're close, but not. That was like 25% of the questions I got asked. Okay. All right, we're going to prove the Cauchy Schwarz inequality.
I mean, rather than those types of questions like ones that are like super rational, right?
Okay, so let's prove the theorem then, if nobody else wants to stop me. Okay, how do you prove the Cauchy Schwarz inequality? It's this is like a nice secret proof that everybody must know, is you do the inner product of x plus some multiple of y. So you do x plus alpha times y with x plus alpha times y, and the thing you know is that this thing in absolute value is going to be bigger than 0. It's going to be bigger than 0. And you don't even need absolute values because it's some real valued thing. That's the norm. This is the norm. This is the norm of x plus alpha y. And then we're going to expand it out, and we're going to see the relationship between the x's and the alphas and the y's by expanding this out, and whatever we get will have to be bigger than 0. That's the basis for the inequality. So let's do it. And this is essentially exactly what I had you guys do in the warm-up problem. That was the case alpha equals -3. Now we're in the case of any alpha. But by the same thing as before, you expand it out, and you got to watch out for bars, x, y, plus alpha yx plus, and this is the absolute value of alpha squared, yy. Okay, and let me fix up this thing. Okay. So now plug in. So this inequality works for every alpha. No matter what alpha you do, you will always get that this combination of the x with itself, y with itself, and the xy's, this combination will always work out to a real number that's bigger than 0. Yeah?
If we're putting a bar over the alpha, would we need to also... Oh, no, never mind. Maybe, actually. Oh yeah, the inner product can be like complex values, right?
In general, the inner product can be complex value, but specifically when you have the same vector repeated twice, it must be real valued and it must be bigger than 0. Actually, like maybe this is worth going all the way back to here and making a note. I think I wrote bigger than 0, but maybe you should say xx is real valued and, right? Otherwise, it doesn't make sense to ask that it's bigger than 0. And that is, like, y actually defines a norm. Norms are definitely always real valued, and the only reason it works is because when you do the inner product of something with itself, that gives you the norm, right? Okay, great question. Okay. Okay, so this works for any alpha, and if you plug in the right thing for alpha, the inequality will pop out. And in fact, that thing for alpha is like minimizing this. Like if you were to plot this as a function of alpha, it's a quadratic equation in alpha, right? And you can find the minimum of the quadratic equation, say by the quadratic formula, or like however you want. And this inequality is the best possible inequality it can be at that minimum. And that minimum is this alpha. Alpha equals minus xy divided by yy. And if you plug that in, you get an equation. That equation is going to have a lot of y's on the bottom. And that's because alpha has yy on the bottom, so you're going to have like a yy on the bottom, a yy on the bottom, a yy squared on the bottom with a yy over there. So the other thing you should do to simplify is multiply both sides of the equation by yy. Okay, and on the left-hand side, you're going to get 0 times yy. And on the right-hand side, you're going to get less than, and you're going to get xxyy. That was the first term, xx, then you multiply everything by yy, xxyy, that's that term. Then there's going to be a whole bunch of terms over here, and all those terms are going to work out to 0. They're going to work out to 0 because alpha has exactly the xy, they're going to like cancel each other out. And so by using the rules, you're going to get a plus 0. So, and this is like cancellations. And then at the end over here, you have the absolute value of alpha squared. That is going to be the absolute value of xy squared because alpha has xy in it. The reason there is no yy is that got canceled away. That also got canceled away. So hopefully it's not too many steps at once, but it saves us some writing. And I have forgotten some kind of sign, because it should be minus. But I'm trying to figure out what I did wrong. Alpha squared, alpha y. Okay. Well, we would really like it to be a minus sign because then it's the inequality we want. With a plus sign, it's negative the inequality. Yeah, that's not good. So I'm clearly forgetting a thing. Oh, okay. I just completely lied to you guys. I said cancellations. It works out to 0. Of course, it doesn't work out to 0. It's going to work out to negative this thing. Okay, let's do that. All right. This is a total lie. This is what happens when the textbook is like, you get this, and I'm like, okay, it must be like that. Okay, let's do it. Okay, so plus alpha bar xy. So plus alpha bar xy. Alpha bar is xy bar. Let's do that with a minus sign. There's still a minus. Okay, minus xy bar times xy. Then we're dividing by yy, but that got canceled away. So there should be divided by yy. I'm not ready because I multiplied both sides by yy. Then over here, there's alpha, which is a minus xy times yx. Okay, and then there's the divided by yy, that got canceled away. So it really is this. Let's highlight the terms. The x-axis is the xx. The alpha squared yy over here becomes this guy over here. And then these terms with the alpha bar in the middle are this and this. Okay, we have 4 terms. Xy bar times xy is the complex conjugate of a number times itself. That's the absolute value squared. So this thing is equal to xx yy plus the absolute value of xy squared minus the absolute value of xy squared. Okay, great. What about this other one? Xy times yx. Anyone know what to do with that one? Yeah. It's a good thought. You can't absorb a minus sign, but you can absorb something else. You're thinking of the right thing, because minus signs flip things, and conjugates also flip things, but they're like flipping in 2 different directions. So it's not flipping in the negative direction. Yeah.
Flip y and x.
That's right. You flip y and x, and that makes a complex conjugate, which is the other type of flip, right? Okay. So you get minus x y, and yx is xy bar, right? That's that kind of flip. Okay, and that is again, xy times xy bar is once again an xy absolute value. Let me just cross it out so we don't have to write everything again. Xy absolute value squared. Okay, So what do we have? We have x, y, y plus one copy of the absolute value squared minus another copy of the absolute value squared and minus yet another copy of the absolute value squared. So what do you get at the end? 1 plus and 2 minuses is you get x, y, y minus the absolute value of the xy squared, which is what I claimed earlier when I lied to you and told you that the things cancel in the middle. They don't, right? They give a negative 2 xy squared, and that goes with the last term to give a negative. Yeah?
Where did the minus sign go for the first multiplication of the conjugate?
In this one right here, this plus?
Yeah.
So it's plus one copy of it, minus another copy, minus another copy. So plus 1, minus 1, minus 1, which gives a minus 1. Okay, let me factor it out. Let's do one more step. Let's do one more step. Plus 1 minus 1 minus 1 times this. Okay? So these three terms are all the same thing, except this one is a plus 1, and this one is a minus 1, and this one is a minus 1. So you get 1 minus 1 minus 1, which is negative 1. Okay, so this is x, y, y minus xy squared. Yeah, this is what the textbook says. The textbook says 0 less than this in one line. Okay, so now you've seen one. Okay. It's good to do it carefully. Yeah. Yeah.
Can you just scroll up for 1 second?
Yes. Okay. The left-hand side is also 0, right? 0 times something is 0. So what do we end up with? 0 is less than this stuff. You move that to the other side. That's the Cauchy-Schwarz inequality. So therefore, the absolute value of xy squared is less than x, y, y. Okay. I think I once got into a fight with my TA when I was taking quantum theory. And there was like, prove the Cauchy-Schwarz inequality. And I gave him this proof. And they wanted some other proof. And he's like, wow, just look it up and do it the other way. I was like, no, we're doing it this way. He gave up. He gave me the mark. Okay. Fun fact, that guy writes children's books about science. So it's like baby's first quantum theory book. Anyway, okay. Enough about my
Look at
life.
look at where you are, look at where he is.
Yeah, you could probably find him. That's
Yeah, it's
very
really
embarrassing.
hard.
Okay.
Just so like just so like hard it is.
Sorry?
It's just so like hard it is.
Yes, if you go to any bookstore and you're like, show me baby books about science, all of the books are written by him. He's the only baby science, and it'd be like thermodynamics for babies, classical mechanics for babies, chromodynamics for babies, just like gravity for babies, yeah. Every single book is good. He's like the only one, yes.
I see the general relativity one.
Yes, exactly. See, there you go. He wrote that one. Yeah. And to his credit, in the end, he did give me the mark. So it's not a bad thing. He just started out as a villain in the. Okay.
No, but aside,
Okay. So this is the proof, and this is like super useful. Like anytime you see, and by the way, the left-hand side is x squared y squared. So if you take the square roots, then you get what we wanted. So if you're ever working with inner products, you should always be thinking about this, especially in analysis class where we want to prove that things are less than epsilon. This is how we're going to do it, right? We're going to convert our inner products into norms, and we already spent months trying to work with norms. Now we know how to do it. This is going to work for us. Okay. There is a corollary, which is corollary 3.2.10, which is the triangle inequality. And you'll notice, if you go back up to the definitions we started today with, there is no triangle inequality on here, right? I did not say triangle inequality. There is no triangle inequality. And that's because triangle inequality automatically falls out. So Cauchy-Schwarz automatically happens from these rules. And if you have Cauchy-Schwarz, you automatically have triangle inequality. So if you have this inner product structure, everything is already baked into it. It works super nice. You don't need to prove anything new. So the triangle inequality says the norm of x plus y is less than the norm of x plus the norm of y, and the proof is to write out, I believe, that x plus y with x plus y is equal to x with itself x with itself plus xy plus yx plus yy. Oh, I'm out of space. Okay, yy. Okay, and then, okay, that's equal to the norm of x squared. The norm of y squared are the xx and the yy. In the middle, you have xy plus yx. But yx is the complex conjugate of xy. So you're adding a complex number to its complex conjugate. And there's a formula, I guess maybe you need to know. Alpha plus alpha bar is twice the real part of alpha, right? This might be a familiar one. Like the complex parts cancel out, right? One of them comes with a plus I, one of them comes with a minus I. They destroy themselves, you're left with 2 times the real part. So plus 2 times the real part of xy. Okay. And the real part of xy is definitely less than the absolute value of xy. So less than x squared plus absolute value of xy plus y squared with a 2. This is, the real part is less than the absolute value. And now this thing is x plus y. Okay, I have to do Cauchy-Schwarz first. By Cauchy-Schwarz, which is often people say by CS, x squared plus 2 times x y plus y squared. And now, this is something you should recognize. Square the first term, square the last, double the product. Math sub last. This is equal to x plus y squared. Okay. So there you go. That's the proof of the triangle inequality because of Cauchy-Schwarz. So like a stronger version of the triangle inequality. Okay. Here's another quick little theorem for you. Theorem 3.3.12. And now we're going to start to do convergence, right? Because it's a norm space. All the stuff we did with convergence in chapter 1 and 2, that still applies. So here's the theorem. If xn converges to x in V, and yn converges to y in V, as norms, like I should say in norm, then the norm of, sorry, not norm, just xn, yn as a number, xn, yn as a number, and that will converge to the inner product with xy. This is in R. Okay. So xn is converging to x, yn is converging to y. That's in the norm space V. And then the numbers xn, yn as an inner product converge to the number xy in R. Let's prove it. Prove it. And to prove it, you have to look at the difference. What does it mean to converge in R? It means something about the difference, xn, yn minus xy. The xn's are changing, theyn's are changing. We're combining the xn and the yn. Here we have xy. Can anyone think of a clever thing we could do here to make our lives a bit easier? This idea would have also helped you on problem 1 on the midterm. Yeah?
You can add 0.
You can add 0.
Specific way.
Yes, in a specific way. Yeah, that's right. What is the specific way? How would you do it? That's exactly what you need to do.
Is it going to be an xn and then a y and then x and then yn, like 2 different?
Yeah. In fact, you can do it both ways. So you can do either way. So you can do x with yn and x with yn, or you could do xn with y and xn with y. Either way would work. But we're exactly adding and subtracting 0 in a smart way. So let's do like minus like this and plus like this. And the point is, we've taken this thing to this thing, we've changed 2 things. Let's change one thing at a time, and that way the difference between this and this only changes one thing. The xn's are the only thing that's changing, and here the only thing that's changing are theyn's. So we've gone from 2 things where 2 things are changing to 2 different things where in each one thing is changing, which makes it a little easier. So now by triangle inequality, so this was like the clever idea. Add 0. Add 0. Right, which is like a common idea that comes up all the time. And now we do regular triangle inequality to split it into 2 things, xn, yn minus xyn, plus, so that's this one, this first one over here, And the second one, we have the y's are changing. So it's x, yn minus xy. Okay, very good. And now because only one thing is changing, and the inner product is bilinear, right? It's linear if you keep one thing the same. Now we can factor things together. So you get in xn minus x with yn, plus, on this side, x with yn minus y. Beautiful stuff. Okay. How could we bound this thing, right? We have some inner products. Oh, it's so annoying. How do we make these inner products go away? How can we control them? Yeah.
xn is approach to x.
Xn is approaching to x. So if xn is going to x, that means we know something about the norm of xn minus x, right? Xn going to x tells us the norm of the difference of the vectors is going to 0, right? But unfortunately, I don't have any norms anywhere on my page. I just have inner products. Yeah.
Use Cauchy's Schwarz.
Yeah, exactly. So we're going to use Cauchy Schwarz now. Xn with x with yn is less than xn minus x with yn. And this one is less than x with yn minus y. And now I'm in perfect shape because I have the ingredients that I have. I know xn minus x is going to 0, and that appears on the page. Here's yn with y. In the textbook, they say it just goes to 0, and they don't worry about it. But let's do the epsilon delta proof to make things rigorous. So now we have this nice inequality, and we're going to prove that the right-hand side goes to 0. Let's do it. So for any epsilon greater than 0, choose what? We're going to choose some n's, and then we're going to make it so that when lowercase n is bigger than capital N, this whole thing is going to be less than epsilon. How are we going to do it? Well, how big should yn minus yn be? So since yn goes to y in norm, choose, let's call it n1. So the norm of yn minus y is less than what? It's going to involve epsilon, but just involving epsilon on its own is not enough. What should we do? Yeah.
Can you do epsilon over 2 times 1 plus norm of x?
You want to do 1 plus norm of x?
Yeah.
Yes. Okay, this will work perfectly. Can you tell me why did you add 1?
Just then norm of x over norm of x plus 1 is less than.
Yes, this is very clever. So most people would write epsilon over 2 divided by the norm of x. And then they're like, aha, see, yn minus y, and then I multiply by the norm of x. And then they cancel out, and then we're like, get an epsilon over 2. Great. Technically, if norm of x equals 0, you've made a boo-boo of dividing by 0. Okay, so it's very, very smart to add 1 so that you don't divide by 0. And the norm of x divided by 1 plus the norm of x is still always less than 1. So very technical. This 1 plus is a nice technical way to deal with this problem. If you forgot to add 1, it's fine. I won't take off any marks. So don't worry if you're having some trauma from question 1 on the midterm. But technically, this is better than my proof. Yeah, I'll just divide by marks. Okay. The next one is a little harder. Since xn goes to x in norm, we're going to choose n2. So what? Xn minus x. Again, depends on epsilon, but what are we going to do? And why is it trickier than the other one? Yeah.
So naively, I would have chosen epsilon over 2 divided by 1 plus the number of yn, but I think that's wrong.
Yeah, okay, this is a great, let's write this. So this is, what I'm about to write down is not right, as you said, but let's write it down because it's instructive, okay? So we're gonna write down something that is wrong because that's how we learn things, okay? So we're dividing by norm of yn. Or if you want to be fancy, 1 plus the norm of yn. So first of all, why is that not allowed? Yeah.
And it's changing.
Exactly, and it's changing. Look, the definition of a limit doesn't say anything about changing the right-hand side, right? It says you fix epsilon, and then I'll find the n. Then it'll work. You can't do this like weirdo stuff where you change the right-hand side as n is changing. The definition says you give me epsilon can be whatever you want, but it's got to be some fixed number. And that's not a fixed number, so that's not allowed. So that's the reason it's not allowed. I stopped you. You probably had a way to fix it. Well, you didn't. Okay, good. That's even better.
I tried to do the midterm, but I don't
Okay.
have a question, so that's fine.
Yes. Okay. So
Since yn goes to y, does
Yeah.
that mean norm of yn goes to norm of y, so it's bounded?
this is the thing you got to do. Okay. So let's all think about it for a second. So this is what we want to do. We would like to do this. And unfortunately, yn is changing. But can we put something that will just do all the yns at once, right? And so this is the thing that I would really like to do, is xn minus x. Why don't we make it less than this, and we'll make it the smallest one. We'll divide by the infimum over n of the norm of yn. And that is less than epsilon over 2 over norm of y for all yn. Right? So the point is, we would like to do it with a yn, that's not allowed. But just like figure out whichever one is the smallest and divide by that one. And okay, again, technically if this is 0, you're in trouble, so better put a 1 plus to cover your bases. But that's the idea. And so why can't this be some big thing? Do I have this wrong? Should it be a soup? So I want it to be as small as possible, but it's in the denominator. So it should be a soup, right? Okay, good. That very good. Okay. That's like, in my notes, I'm pretty sure I wrote soup. Let me go check my notes. Because when we get in trouble, we rely on past Mihai to bail us out. Okay. Okay, yeah, soup. I have soup. Okay. So we take the largest possible norm, we divide by the largest possible thing, and that's definitely less than dividing by something that is small, right? And that way it doesn't depend on n. But there could be one problem, which is y is soup n of norm of yn less than infinity. This is like a question you would have to answer, and the reason is because yn is converging to y, right? So since yn goes to y, we know norm of yn goes to norm of y. So like eventually in the sequence yn, it's within, say, 1 of norm of y. And if it's eventually within 1, then what is the soup? Well, it's less than the first bajillion terms, and then norm of y plus 1. So norm of yn is bounded. And if you wanted to prove this more carefully, you could say, let epsilon equal 1 and choose capital N. So n greater than n implies norm of yn less than norm of y plus 1. And then the soup n of yn is less than norm of y plus 1 plus the maximum of the first capital N terms of yn. So there's like a full proof of why it's bounded if you want. But for sure it would be enough to just say it's bounded. Yeah?
Oh, what's in the, to the right of the inequality, the right of the less than or equal to, you got the yn.
Oh, for all yn? This one?
Sorry, a little bit lower and then a little left.
This way?
Down,
Yeah?
right? That guy.
Well, the norm of yn is less than the norm of y plus 1. So I put epsilon equals 1.
Thank you.
Yeah.
Just couldn't see it this version.
Okay, yeah, it got let's fix it. I see people squinting. I get it. Okay. The soup n of the norm of yn is less than the maximum of the first capital N. Let's say n less than or equal to n1 of yn. Okay, here, let's do it this way. You do the maximum of the first few, and then you do norm of y plus 1, and you take the maximum of everything. Okay, let's do it that way. So this is a proof that a convergent sequence is bounded, because how big could the norm be? Well, eventually, after n1, we're all less than y plus 1. So you can't get any bigger than y plus 1 from all the infinity numbers, n1 plus 1, n1 plus 2, n1 plus 3, and so on. And then you also have the maximum of the first n. That's some finite number, right? You take the maximum of the first n, take the maximum of the last infinity. That's the 9. Okay. Did I call it n1 at least? Let's call it n1. Okay. Okay. Yes.
Once again, what is immediately to the right of this new inequality sign?
Of here, right here.
Yeah, that little guy.
That's max.
Okay, thank you.
Max.
Max, the max of the max. Huh?
Max.
Max is no eyes.
There, you happy? All right. Yeah, max, maximum, or the good name for a dog. Okay. Okay. Where are we? Okay, we're at like layers deep. Okay. So we do it with the soup, the largest possible. This is totally how I do it, and so I would write this. So this one is no good because it depends on n. This one doesn't depend on n. So choose n2. So this. And then once you have that, then when you multiply them by these things, the whole thing is going to be less than epsilon over 2 plus epsilon over 2. And I guess I should also write choose this such that this for all n greater than n1, for all n greater than n2. And then if you take the maximum of n1 and n2, then past that point, it will all work out. So for all n greater than the maximum of n1, n2, the norm of xn, yn minus xy is less than epsilon over 2 times 1 plus the, which one was first? I think this one was first. Sup n of norm of yn times yn plus epsilon over 2 times norm of x plus 1 plus times norm of x, and that whole thing is less than epsilon over 2 plus epsilon over 2 equals epsilon. Okay. And I guess, okay, this should be a less, strictly less than. Okay. So there you go. There's like the full proof, even including the proof that a convergent sequence is bounded, which is a great, great thing to know. Why did we go into so much detail? Because this is basically the solution for problem 1 on the midterm. Now you know. Most people got it, I think. Okay. Questions, comments? Okay, so we're gonna stop there. Next class, don't come here on Tuesday. On Thursday, you'll do some more Hilbert space stuff from the book with the other Professor Nika, and then yeah, then we'll have the week after that. We'll finish up with the Fourier series stuff. Okay. Oh, and yeah, make sure you think about your project and consider signing up for the thing. There's also, in the form, it tells you what day you are present. So the sooner you think of a project, the sooner you can fill out what day you are present. Okay.